Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives, so specifically we're going to continue talking about optimization. We're going to do a couple harder problems that work with angles and trig, so everybody's favorite. Let's go ahead and dive into it. Number one, suppose you're standing on the shore of a circular pond with a radius of 1 mile and you want to get to a point directly opposite of your position. You plan to swim at 2 miles per hour from your current position to some other point P on the shore and then walk 3 miles per hour along the shore to the terminal point. How should you choose P, the point, to minimize the total time for your trip? So our first step is to always draw a picture. We're given lots of information here, so let's go ahead and draw a circle. And let's go ahead and say that we are wanting to start right here. So this is our start, and we want to finish directly opposite of our starting point. So what this lady wants to do is she wants to choose some point P along the curve. So let's just go ahead and say this is our point. So first she's going to go ahead and swim there. So she's going to swim directly across. And then once she gets to the shore, she's going to go ahead and walk the rest of this distance. So she's going to walk to the finish. We want to go ahead and choose P, this point, so that the amount of time it takes is super short because they swim and walk at different rates. So there are some formulas that we need to have. First, let's talk about the formula for walking. As we walk along the shore, we're going to have to use the arc length formula, which is equal to the radius times the angle. So let's talk about what the angle is going to be. We have from P to the origin, we have that the radius is equal to 1. So there's going to be some angle from the start to the point P, and we're going to go ahead and call that theta. So then in order to find our corresponding angle for where we walk, we're going to have to use pi minus theta. And so that's going to be our angle we use for that. Now, to talk about where we're swimming, we're going to have to use a formula for a chord. So this is called the chord of a circle, and the formula is given as 2 times the radius times sine of theta divided by 2. So now that we have all these formulas laid out, let's go ahead and talk about how we can find time. So there's a formula we have for time. Time is equal to the distance traveled divided by the rate in which we're traveling. So when we talk about swimming time, like we said, when we swim, we're going to use the formula for a chord. So this is going to be 2 times the radius, which is 1, times sine of our angle. In this case, we called our angle right there theta, divided by 2. And then we're going to divide it by the rate at which she swims. And if we look back at the original problem, she swims at a rate of 2 miles per hour. And so we're going to divide by 2. If we simplify this, this is just equal to sine of theta over 2. So we're going to do the similar thing for walking time. We're going to take the distance, and this is going to be arc length. So we're going to take the radius of 1 times our angle. And like we said, our angle for walking is going to be pi minus theta. And so this would be pi minus theta. And now let's go ahead and divide it by the rate at which she walks. And if we look back at our problem, she walks at a rate of 3 miles per hour. So we're going to divide this by 3. We can simplify this. This is equal to pi over 3 minus theta over 3. So now we have our 2 times, and in order to find the total time, it's going to be those two added together. So let's go ahead and make an equation. We're going to have time of theta, because we're in terms of our angle, is equal to, and there we have it. We have our equation. We finally made it. So all of that setup was for the equation, and we had to use quite a bit of geometry, actually, these different formulas, try some trig in order to get there. So remember, we want to now go ahead and find our critical points. So that means I'm going to take the first derivative of this, so t prime of theta. And so let's take the derivative of sine. So the derivative of sine is cosine of theta over 2. And now we have to multiply by the derivative of theta over 2, which is just going to be 1/2. The derivative of pi over 3, remember pi is a scalar, so this is just going to be 0. And now the derivative of theta divided by 3 is 1/3. So here we have our simplified form of the derivative, and remember, we want to go ahead and set this equal to 0 and solve for the critical value. So I'm going to go ahead and do that. Okay, this is for sure a calculator problem. I used it. I got 1.68 radians. This is our critical value. So actually what I'm going to go ahead and do now is talk about the second derivative test because I want to know the concavity. If it's concave up or down, that tells me if it's a maximum or a minimum. So I'm going to go ahead and calculate the second derivative. Okay, so we have our second derivative. And so of course we want to find our inflection points. So we're going to do that by setting it equal to 0. If I multiply that negative 1/4 over, I still have cosine of theta over 2 is equal to 0. we can take the inverse cosine of both sides, and so I get this. And let's think about the angle at which cosine is 0. That's going to be at negative pi over 2 and positive pi over 2. If we look back at our angle is actually going to be strictly between 0, and so that would be if we had our starting point right here, and between pi, which we extend all the way out here. So theta is bounded between 0 and pi. So that means our negative pi over 2 isn't going to make sense. Instead, I'm going to just go ahead and use that pi over 2. Multiplying both sides by 2, I get theta is equal to pi, which is actually very nice because we're bounded by 0 and pi. So our interval is just going to be this right here. So remember, we want to test points from our interval. We're going to plug it into our second derivative. If it's negative or positive, that tells us if it's concave down or up. So let's just take a value just strictly in the middle. I'm just going to choose pi over 2. And I'm going to go ahead and plug that into my second derivative. I'm going to stop right here because all I care about is if it's positive or negative, which I can see it's a negative value. So if it's a negative value, that tells me that my function is going to be concave down. So let's talk about what this means in terms of our critical value. We found that on this entire interval, it's concave down. So it's going to look something like this. At our critical value, it's going to be a relative maximum. And a maximum tells us we're maximizing the amount of time it takes to get from the opposite, you know. So we actually don't want to use this value. Actually, what we're going to look at is the endpoints. We have an endpoint at 0 and an endpoint at pi, because right here, the total time is going to be minimized. So it's either going to be quickest to just walk all the way around or swim straight through. So let's go ahead and plug those back into our original function. I'm going to rewrite it. Let's plug in our endpoints. Okay, so if we look at the difference between these two values, first we got a value of 1.05 hours, and then we got 1 hour. So as we can see, our time is optimized when our angle is equal to pi. So if we think about this in terms of our context, I'm going to go ahead and redraw it. Here's our pond, right? And we are starting right here and we're finishing right here. If the angle is pi, that means our point is also going to be our finishing point. And so this is telling us it makes sense for her to just swim all the way across because that's going to save the most time. So let me go ahead and write that out. So to answer the question, it said, how should you choose P to minimize the total time for the trip? Well, I should choose P to be my finishing point to minimize time to 1 hour. So that's all I have on this problem today. If you enjoyed this video, I have many more like it, so make sure to check out my previous videos. They're linked down below. Otherwise, please leave this video a thumbs up and comment other topics or problems you'd like to see done. Thanks for watching.